Hello, my name is Henry Corrin. I am the Chief Product Officer of Imatest. Today we're going to be talking about stray light or flare testing. And I'd like to introduce Jackson Knappen, who is an imaging scientist at Imatest and specializing in flare, stray light. And go ahead, take it away, Jackson.
All right, thank you for the introduction, Henry. So today we're going to be talking about stray light testing and Imatest solution. So just an overview of the contents of this presentation. It's going to take about 20 to 30 minutes, and then we'll open the floor to questions. We'll start with some background on stray light, and then an overview of the existing tests. Then we'll follow that up with new tests, or how we're proposing to test for stray light, and then going over our equipment and software. So start out with some background. First of all, what is stray light? The definition is any light that reaches your focal plane or your image sensor via a non-designed optical path. And that's the definition from some of the upcoming standards, such as IEEE P2020, which we'll get into a little bit more detail later. You can think of stray light as systematic scene-dependent optical noise, in that it can change or will change depending on where the source of light is relative to your camera. And stray light and flare are interchangeable terms. They're largely used by different communities. Stray light has been used by the aerospace and defense industry. Flare is classically used by the consumer photography industry, and more recently, the automotive industry. Veiling glare is a type of stray light. That's another similar term that's tossed around. So here are some examples of stray light that clearly show the issue. I want to highlight the top left image. You have some interesting stray light artifacts going on the right side of the image. And then you have veiling glare, which is leading to an overall loss of contrast throughout the rest of the image. Then moving over to the top right, we have that picture of the birthday cake. There's a very clear example of ghosts or ghost artifacts here, where you have basically a perfect reflection of the candles going on somewhere in the cake. So that's an object that's not actually there in the scene. It's a ghost reflection. And then I want to highlight this picture in the center bottom, this one of the traffic light. This is an image I took relatively recently, and you can see there's the sun in the field of view, and it's leading to a stray light artifact that is somewhat covering the traffic signal, which isn't good. And then you have all these other specular highlights and color shifts that are in part caused by contamination or debris on the windshield. So why is stray light a problem? Those examples kind of demonstrate that, but first, contrast loss due to veiling glare. The stray light will effectively decrease the dynamic range of your camera. That could be the bottleneck or limiting factor. It can also produce a false signal for your dynamic range testing or SNR testing, so it will effectively increase the measurement or the signal for your dynamic range test, which is going to give you a false measurement or an overestimation of the dynamic range. It'll lead to false features in the scene. You'll literally see objects that aren't there, i.e. ghosts, and changes in colors, which can be undesirable. You could say that not all stray light is bad. For cinematography and artistic photography purposes, some people like stray light. You'll see a lot of that in Michael Bay films, for example. But it's becoming more and more of an issue now because of the applications the cameras are being used in, for example, automotive, and also because image sensors are becoming more and more high dynamic range, and higher dynamic range sensors are actually more susceptible to stray light. If you think about it, you'll be able to see a larger range of light. So if you have an imperfect lens that's producing flaring, you're going to be able to see that or more of the flare if you have a higher dynamic range sensor. What can cause stray light? There are a lot of potential causes. I am not an optical engineer, so I cannot go into detail into all of these, but you'll have reflections off of various lens elements or the housing for the lenses. You could consider diffraction spikes to be stray light. Filters, lens coatings, those types of things can produce reflections. There's a whole lot of issues or design, optomechanical design things that can lead to stray light. So now I want to briefly talk about the existing stray light tests that are already out there. First, we have ISO 9358. This is an optics only stray light test. So it's meant to test individual lens elements or lens groupings. And yeah, it's not a system level test. I consider this a predecessor of the new generation of stray light tests that we're talking about today. So it requires a reference detector that has undergone radiometric calibration so that you can get some absolute measurement of the amount of stray light. We also have ISO 18844. This is probably the most well-known stray light test, but it's really a limited test. So it involves a backside illuminated chart with these dots in an X pattern that you see in the bottom left figure here. This test is okay for measuring veiling glare, but it's got some limitations that, one, it's not considering sources of light outside the field of view of the camera, which is important. You can have stray light originating from outside your field of view. It's not defined outside the visible spectrum, so it's not taking into account infrared or anything like that. And it also uses very limited analysis points. So you're only able to quantify stray light within these circular patches, so that there's a limited amount of spots that you can actually analyze here. Imatest does support this type of analysis via our flat field module. And this is still being continued today. IEEE P2020, for example, does have a method that is similar to this. So now I want to talk about the new and upcoming tests for stray light testing. And this is what we're mainly talking about today, is this type of test. So here's an overview of the test method. It's quite simple in practice. All you're doing is you're capturing images of a small bright light source in a dark room. And then if you want to build field coverage, you can rotate the camera, or you could rotate the light source around the camera, capture multiple images. And then what you'll do is you'll take those captured images and process them into what we're calling normalized stray light metric images, which is that nice graph up top. And in these metric images, you mask out the light source object itself, or the main projection of the light source, because ideally that's all the camera should see, right? If you're pointing your camera at the sun, ideally it should just see a circle that is the sun, but in effect you'll see, a lot of blooming and a lot of flare, and that's what we're trying to measure here. This method of stray light testing is meant to correspond with the upcoming standards, IEEE P2020, and there's a new ISO 18844 method being developed. So just taking a closer look at the data that's shown there, this is how we captured it. So this is, there's a GIF of our test lab on the right, where we've got a camera mounted to a motorized gimbal placed in front of a light source, surrounded by blackout curtains. And we're just taking images of the light source at different camera angles. And you can see there's different axes sweeps going on here. So there's a horizontal sweep and also a diagonal and vertical sweep at the light source. You could test with just a single axis sweep, but with that, you're assuming radial symmetry, and you might have radial asymmetry or asymmetric stray light performance due to imperfect optical design. You might have some deviations on the surfaces of the lens that only cause stray light at specific azimuth angles and field angles. So for comprehensive testing, you would want to be positioning this light source at as many positions as possible in and outside the field of view. But that will take time. So as I mentioned, there's these new developing standards. They're still in development largely. Imatest is actively involved with some of these, and we're committed to supporting standards. Some of these include IEEE P2020. This is an automotive image quality standard. It's currently in the pre-release stage, and we're expecting a first initial release at sometime in 2023. ISO 18844 is also developing a new method that is very similar to the IEEE P2020 method. And I am not exactly sure when that will be released, but it's being worked on. There's also some other standards. There's a China standard. There's IEEE P4001, which is a hyperspectral standard. We know they're developing a new method. And the ISO TC172 group, the same group that made the ISO 9358 optics only test, we know that they're looking to update their standard. So there's a lot of development in the community going on right now involving this test method and getting it standardized. A little bit more detail on P2020. Again, it was pre-released and we're expecting a release in 2023. It defines two methods for measuring stray light. Method A is very similar to ISO 18844 with the backside illuminated chart. But method B is similar to what we're describing here today. It uses a new metric called flare attenuation. And it says that you can either rotate the device or you can rotate the light source around the device under test. So now I want to talk about the Imatest stray light testing solution, our equipment, how we're planning to accomplish this testing. So to test for stray light, quite simple. You really only need three things. You need a dark or a black room to test in. You need a small bright light source, and you need a way to rotate the camera under test, or alternatively move the light source around the camera. Imatest is taking the modular approach here, so we're opting to rotate the camera, at least for now. So there's a motorized gimbal picture here on the left where you have two axes of rotation, and we're also developing some light source options. Here on the right is a highly configurable light source that we're developing with a company called LabSphere. A little bit more detail on the motorized gimbal. So the two axes of rotation it provides are camera roll and yaw. And these, when set up and aligned properly, will correspond with the light source azimuth angle and field angle. I'll get into a little more detail on those terms in the next slide. So this is just meant to provide accurate, flexible movement. So 0.08 degree accuracy. And then we mount this on top of a goniometer to help with camera to source alignment. The figure on the right is a little misleading. The front of the camera, the very front, including like the end of the lens hood, should be positioned at the center of rotation for stray light testing because you're trying to minimize the projection, the area of the projection for the test, though I don't think I'm explaining that quite well. So if you have an optics background, you're probably familiar with these terms, field angle and azimuth angle. This is just demonstrating what they are. Field angle is moving radially outward in the field, right? And azimuth angle is rotating around in a circle. So this is how you would do the bookkeeping for your data collection here, using these two terms, azimuth angle and field angle. And that's how some of these standards are requiring the results be reported. You would have a metric image associated with a specific light source azimuth angle and field angle. So as for the light source, there's a lot of different options. One option is to use a basic multi-purpose fiber optic illuminator, which is what we have here. And we put this on a benchtop setup where we have the light source mounted to a 2-axis goniometer to help with alignment on top of a metric optical breadboard. And then the motorized gimbal with the camera is positioned downrange. So you can test with a diverging source like this, so long as the setup remains constant. And by setup, I mean the camera to source distance and also the alignment of the camera within the beam of light. then you should be able to get repeatable stray light testing. But if you move anything, you might get different results. So that's the drawback. So this source is meant to cover both visible and near infrared. It has a collimation optic attached to it, but it doesn't really perfectly collimate the light. It rather focuses it into a narrower, albeit still diverging beam, which helps to reduce the amount of extraneous reflections around the scene if you've got a narrower beam. So this setup is actually already available on our store. But we're also developing this configurable light source with a company called LabSphere, which is that company is very involved in the aerospace and defense industry. And we're designing this specifically for stray light testing. So it has a small integrating sphere with a radiance monitor detector mounted to it. So that allows you to generate a highly uniform and highly controlled light output. You can keep track of exactly how much power is being output from that sphere. And it has 3 ports for swappable LED engines. So these 3 protrusions off the sphere, these are the LED engine ports. So you could, for example, combine visible LED with infrared LEDs, but there's also other wavelengths available. So the idea is that it's highly configurable to whatever spectrum you want to test with. It's also got adjustable optics on the front, which the purpose of those is to collimate the light, but it can also produce diverging light. And then inside those optics is a adjustable iris. And that lets you change the size of the main projection of the light source or the light source object that is viewed by your camera. We're expecting this to be ready in the beginning of 2023. If you're not familiar with integrating spheres, the inside of the sphere is coated with this highly reflective material that's reflective throughout a very broad range of wavelengths. So in theory, you should be able to plug in really whatever spectrum or LEDs you want within this range, and the sphere will combine that light and produce, a single uniform light source. So that's the idea there. And if you're not familiar with these diverging and collimated terms, so collimated, you have all of the light rays emanating in the same direction, and it's basically simulating a light source from infinity or infinitely far away. And the diverging source, it's still useful because you might have a larger camera or a larger system that you need to overfill. So the idea is you overfill the front of the camera with light, but if you've got an automotive camera with maybe a windshield in front of it, it's going to be really hard to produce a large collimated beam of light. So you might need to use diverging light to be able to overfill some of those larger systems. And then this is demonstrating the effect of the iris or the source object size. What we've seen here in the lab is that using extended light sources, so larger angular extent, will produce blurrier stray light artifacts or more akin to veiling glare. And these artifacts are representative of the stray light over the area that's covered by the source. So on the left, this light source has an angular extent of around 1/2 degree, similar to the sun. And you can see it's producing these sharp artifacts. It's very clear that there's this type of weird petal flare surrounding the light source, and then this shower type flare emanating from it. And then on the right, you see all of those same stray artifacts are present, but they're highly blurred because they're representing an average over the area that the source obtains. So it's really important to consider the light source you're using. Now I want to talk about the Imatest stray light analysis software. So we released a stray light analysis feature in our most recent 22.2 release of the software. And we're going to give an overview of the features. So the workflow is pretty simple. You capture those images that we talked about, and then you can select them in Imatest, or using Imatest IT, the API, and that will generate the stray light metric image outputs along with a bunch of other supplementary outputs. So the main output of the analysis are the metric images. And then anything else, the plots, histograms, etc., those are derived from the metric images. But you'll gain the most insight by looking at the metric images themselves. So what is the actual metric? For the 22.2 release of our software, the main metric we're going with is called point source rejection ratio, or PSRR for short. This is a metric that's actually been used by the aerospace and defense industry for decades, used to characterize telescopes and satellite systems. We found papers and manuals going back to the 70s that talk and utilize this PSRR metric. So the idea is it's a normalized metric with values of 0 to 1, and the calculation is quite simple. It involves taking an on-axis image of the light source, so what's pictured in the top left here, that's an on-axis image, and then taking the level within the main projection of the light source, and then using that level to normalize the rest of the data. So all of the rest of the image data has been remapped to represent this PSR metric. So every pixel in the image now represents a metric in the image on the right. And then within that metric image, we mask out the light source because, again, that is not straight light. Ideally, all you should be seeing is just that little small circle in the center, but everything else is straight light. So ideally, you should be normalizing by a value that is not saturation. In this case, we're normalizing by saturation level, right? The image in the top left is saturated in the center, so the normalization factor is 255 or whatever saturation is for this camera. So ideally, you should be normalizing by something that is not saturated. You could take an on-axis reference image using a different exposure level or light level, or with an ND filter in place, and that will let you normalize by something that is not saturation and be able to get something more objective and meaningful and comparable. So as I mentioned, the PSR metric images, that's the main output, and you can view them as movies. You can output these movies in the form of GIFs or AVI MP4s, whatever you want. This is the easiest way to assess your stray light, right? You can gain the most amount of insight just by looking at these images rather than, pointing to a specific number or a derived metric. You can see what's going on. You could maybe back out, there's a certain optical element or coating that's causing this stray light artifact. So this, as we see it, is the main output and the most useful output. They're also fun to look at. Here's an example of a near infrared result. So this is a camera that's sensitive to near infrared light. We're using near infrared light, and it has a 185-degree field of view fisheye lens mounted on the camera. So this GIF is showing a 220-degree horizontal sweep of the light source. We're using increments of 1 degree, and you can see specific stray light artifacts show up at very specific field angles. There's some stray light artifacts occurring outside the image circle too. A lot of interesting stuff going on. In this GIF, we're not masking out the light source just to demonstrate basically how cool it looks. A lot of stuff going on there. It's a little low resolution, unfortunately, but there is a higher resolution version of this GIF on our website in our documentation if you want to take a look. So again, with these metric images, they can be outputted as FITS files. This is an astronomy data format. So it's designed for storing scientific image data. So rather than your classic image file like a JPEG, which has values of like 0 to 255, unsigned 8-bit integers, you can store floating point data in these FITS files. So it's really useful for scientific image data. And the nice thing is that because this is so often used by the astronomy community, for example, the images from Hubble Space Telescope or James Webb Space Telescope, those are probably shared and passed around in the form of FITS files. The astronomy community has developed these tools, such as this one picture on the right called DS9, that are really useful for digging into the FITS file data and manipulating the data to be able to extract as much information as possible. So in this case, on the left, we have an input image that really shows very little straight light to the eye. But if you load the output metric image fits file into a program like this, you can manipulate the scaling to be logarithmic or different color mappings. And you can really go into some hardcore analysis on your data if you're utilizing these fits files. You can also read them in programmatically in whatever programming language you like and do supplemental analysis there. There's also these supplemental outputs, the histograms and the plots. They're derived from the stray light metric images, but you might be able to plot something that could provide some high-level insight to the data. So in this case, we're plotting different percentiles of the metric images. So we're plotting mean, 50th percentile, 75th, 95th percentile. And you can plot really whatever percentile you want with our software, but you can see there's a clear jump at the edge of the field of view here that's shown by this plot. So you might be able to gain some high-level insight there or set some pass-fail criteria based off these metrics. The histograms are also interesting. These are, in essence, showing the distribution of stray light in the metric images. We're not exactly sure how these will be utilized yet by users of our software, but we think they could be useful, and we're excited to get this type of tool in the hands of people who are actually testing this to see how much use they can get out of things like this. And of course, we also provide standard output files with all the summary statistics and information you could ever want. So in the form of JSON encoded text files or CSV outputs. We're also able to output a file format called HDF5, which is another astronomy file format commonly used by NASA. And this will contain all of the data, including the metric images, the images themselves. So if you're taking a ton of data and you're storing it and passing it around, that might be the most convenient way to do that. So now I want to talk about just some observations on the limited set of results we've shown here. Something important to point out and to consider anytime you're doing stray light testing is coverage or resolution sampling, both the extent and delta of your coverage. So the left and right images here, they differ by only 1 degree, but there's certain stray light artifacts that only appear in one image versus the other. This perhaps isn't the best example of this, but it's very often the case that stray light artifacts only appear at very specific positions. So for very comprehensive testing, you might need to do even smaller increments than 1 degree, depending on the field of view of your camera. So in some cases, field angle increments of maybe 1/10 of a degree might be necessary if you're trying to catch everything. Another observation, it's pretty common that stray light can occur with the light source positioned at an angle outside the camera's field of view. So it's important to test for those cases. In this case, we have the light source outside the field of view on the left side of the camera, but there's some stray light appearing on the right side of the image when it's well outside the field of view. So something important to point out. Another observation is that your stray light can differ completely depending on the color channel you're looking at. So in this case, for this camera, the red channel is particularly susceptible to this petal flare artifact, while the other channels are not as much. So take into account the sensitivity of your camera and which color channels it has. You might need to be looking at specific channels to measure stray light. Another observation, really you should be doing or using linear image data to analyze stray light. Here we have a processed RGB image that has gone through the camera's ISP on the left, and then an equivalent unprocessed or linear image on the right. And if you're using non-linear image data, like the one on the left, you'll end up having these artifacts, such as the banding, these triangles in the left image, that are being quantified as stray light, but they're not actually stray light. So that's a problem, and that's why you should be using linear image data for one reason when you're testing for stray light. So those are the main slides we had to present here today. This stray light analysis feature in our most recent release is really a step towards defining and supporting this new generation of standards, IEEE P2020, ISO, and more. We're committed to supporting these standards and also being involved in their development. So we're really excited about this. There's a link to our documentation page here and on the next slide where you can learn a lot more about stray light and how it works in Imatest. We're still fleshing out some of this documentation, so I encourage you to look at it. And yeah, we can open the floor for questions now. Thank you very much for listening.
Thank you, Jackson. So people can raise their hands or paste questions in the chat, and we're happy to answer them. Let's see. Okay, let's see. Saddam, go ahead and ask your question if you want to unmute. Saddam, can you unmute and ask your question if you have one? Or any other questions people have?
Yeah.
Okay, I can hear you.
Yeah, thanks. Perfect. Good. One small question related to the background of mathematical calculation of the flare. How it is calculated? This because we have movable image, okay, and we are looking on the whole image, but mathematically, this we are summing all the points of the calculated image to calculate the flare, or how it is calculated mathematically. Thank you.
So the calculation is actually really simple. I think stray light is hard to measure because of the bookkeeping, but the calculation itself is really simple. If we go back to this PSRR slide, all we're really doing is a normalization. So we're just dividing the image data by the normalization factor. That's really the main calculation here. So the metric, every pixel in this image on the right, all it took to calculate that metric is to divide the original image data by the level within the on-axis main projection of the source.
But there's no further calculations like luminance and so on?
So there are other metrics out there. If you want to do the bookkeeping of measuring the illuminance or irradiance at the location of the camera, you can and you should do that. There's some metrics like the flare attenuation metric in the upcoming IEEE P2020 standard that do utilize radiometric measurements like illuminance to normalize the data.
Okay, thank you.
Next question we had from Sean. Sean, do you want to, I can unmute or let's see, allow you to talk, and you can ask your question or I can read it for you, whatever you like.
Sure, yeah, no, I was just curious to know how the normalization factor is calculated when the light source is out of the image, off the image.
Yeah, so the on-axis reference image, that normalization factor derived from this image is used for all of the rest of the data, including all of the other images. including those where the light source is outside the field of view. So all of the metric images in these GIFs are normalized by the same on-axis normalization factor.
Okay, thanks.
Let's see, any more questions? Let's see, I think you see Liu has raised their hand. You can go ahead and unmute and ask your question.
Oh yeah, sure. My question is, if you go back to the previous PSRR slides, I think you mentioned that for the normalization, you will keep the center below the saturation, right? So my question is, then the any straight line you're catching will be limited by your dynamic range. I mean, in other words, I guess what I'm trying to say is, if you keep your center below the saturation level, and you use that to kind of try to capture the straight line, then in the reality, if there is a light source that is much stronger than heavily saturated, the much stronger than what you have using here, then there could be areas that has the straight line that you can't capture here, but it will show up in the real world. Isn't that right?
Yeah. So I think I understand your question. So if I were to take this on-axis reference image and it was not saturated, then I probably wouldn't see all this stray light surrounding it, right? So the idea is to take a separate image where you change the level of the light source. And then if you know how much that level changed and you're using linear image data, you should be able to back out the normalization factor from there. So I could either take the on-axis reference image with a different known exposure level, or take the on-axis reference image with a different known light source level where I measure the illuminance or irradiance at the device location for both cases. And then for all of my other images, I do saturate the light source and it produces this flare, but I can still normalize by that other normalization factor if I know how much the exposure has changed or how much the level of the light source has changed.
So then the question is, how saturated you should set it to then?
Well, I think it depends on your source of concern, right? So if it's the sun that's your primary source of concern, you'll probably want to match, like, what are the exposure levels or integration times that your camera is using in application where it would encounter the sun and might be saturated. And then you would want to test with those exposure levels or those light intensities, I think.
So this slide shows the difference between a very bright source that's saturated and one that's not so saturated. And so on the left, you get the ability to measure the faint stray light patterns, but you lose the ability to measure stray light near the source. With the shorter exposure, you can measure stray light close to the source, but those kind of larger patterns are not visible. So it might be necessary to test at multiple light levels to fully characterize your system.
So you are saying that you have to test at multi-level. Is your software be able to capture automatically kind of correlate those straight line images due to different exposure levels and then combine them together, or it's something that we have to take care of ourselves?
So there's a setting in the software that allows you to add in an ND filter value or transmission value. So that would let you back out, maybe if you're using an ND filter, you could back out the density of the filter or the transmission of it. Or if you're using a different light level or intensity, you could calculate the transmission difference there and use that. But there's no way to combine right now in the analysis or in our outputs, there's no way to combine the different results from the different exposure levels that you would see here at the bottom of the slide. It's really it's a high dimensional problem, stray light, right? You've got different wavelengths that might have an impact. You've got different exposure levels, light intensities, and then also the two dimensions, that is the position of the light source with respect to the camera. So that makes it really hard to do because of the amount of bookkeeping involved.
And so I guess, you know, by doing this kind of comprehensive mapping of that space, the goal is to try to identify certain angles of light coming into the system that are problem areas that could lead to misdetections or false detections, which could impact your computer vision performance and, you know, impact the safety of your camera if it's a safety related item. So that's kind of our the rationale behind doing this super comprehensive test where we're, you know, testing, you know, thousands of different points is to see where those failure modes are. So I think that's all the questions that people have asked. Let me make sure that there's no unanswered questions. Very much appreciate your time and hope it was a good use of your time. And we would be happy to speak with you if you're interested in this solution or anything else. And I think that's going to be the end of our event. Thank you, Jackson, and thanks to the Imatest team for all the hard work on this development feature.
Thanks,
Have a great day, everyone.
Thank you.
Thank you.